Hello viewers, in this video we are going to see three-phase voltage source inverter in 180-degree conduction mode with delta connected load. The circuit of the three-phase inverter is shown here. It consists of 6 switches with 6 diodes connected in anti-parallel. The diodes will play a role only if the load is RL or RC load. We have considered here only the R load, so the diode will not come into conduction for R load. This inverter can operate in 6 modes. That is, each mode will be of duration 60 degree. And in 180 degree conduction mode, each device will be in on condition for 180 degree. And the switches are numbered in the order in which they are triggered. S1 is triggered. If S1 is triggered initially, then after 60 degree interval, S2 is triggered, then S3, then S4, then S5, and then S6. The 6 modes of operation are listed in the table. The mode 1 will be there for 60 degree duration from 0 to 60 degree. During that mode, the switches which will be in on condition are S1, S6, and S5. Then in mode 2, the switches which are in the on condition are S1, S6, S2, then S1, S3, S2, then S4, S3, S2, then S4, S3, S5, and then S4, S6, S5. Now let us see the modes one by one. This is mode 1. In mode 1, the switches which are in the on condition are S5, S6, and S1. So the circuit which is drawn here with S1 in the on condition from the first leg, S6 in the on condition from the second leg, and S5 is in the on condition from the third leg. We have this delta connected load, delta connected load. Each load, this is a balanced load with R ohm per phase. We can see here that the A terminal of the load is connected to the positive terminal of Vs through S1. B terminal of the load is connected to the negative terminal of Vs through S6. And C terminal of the load is connected to the positive terminal of the Vs through S5. So we can directly write the voltages across the branches of the delta connected load. The voltage VAB can be written as equal to Vs because A terminal is connected to plus of Vs and B terminal is connected to minus of Vs. So the voltage that appear across A and B terminal is plus Vs. And we can write the BC, voltage across B and C terminals, as equal to minus Vs because B terminal is connected to minus Vs terminal and C is connected to the plus of the terminal Vs. So VBC is equal to minus Vs and VCA is equal to 0. Why? Because these two terminals, A and C terminals, they are short circuited by the switches S1 and S5. So it's S1 and S5, they're both conducting. A and C terminals, they are being short circuited by the conducting S1 and S5, so that VCA is 0. Then we can see mode 2 operation. During this mode, the switch S1 in the first leg will be in on condition. S6 in the second leg will be in on condition. And in the third leg, S2 will be in the on condition. So we can see here that the A terminal is connected to the plus of Vs through S1, and B is connected to the minus of Vs through S6, and the C terminal is connected to the minus of Vs through S2. And so we can write VAB, which is equal to, since A is connected to plus and B is connected to minus, we can write VAB is equal to plus Vs, and VBC, we can write it as 0 because B and C terminals, they are being short circuited by the conducting switches S6 and S2. So B and C terminals are short circuited. So VBC is equal to 0. And VCA, we can write it as minus Vs because C is connected to the minus terminal and A is connected to the plus terminal. Then in mode 3, this is the circuit for mode 3. A terminal is connected to the plus of Vs through S1. B is connected to plus of Vs through S3, and C is connected to minus of Vs through S2. So we can write VAB. We can see here that A and B terminals, they are being short circuited by the conducting switches S1 and S3. So VAB can be written as 0 and VBC can be written as Vs because B is connected to plus of Vs and C terminal is connected to minus of Vs. So VBC can be written as plus Vs, and VCA is equal to minus Vs because C is connected to minus Vs and B is connected to plus Vs. Sorry, A is connected to plus Vs. So VCA can be written as minus Vs. In the same manner, we can write the voltages for mode 4 as VAB equal to minus Vs, VBC is equal to Vs, VCA equal to 0. And for mode 5, when the switches S3, S4, and S5 are on, VAB is equal to minus Vs because A is connected to the minus of Vs and B is connected to plus of Vs. So VAB is minus Vs. VBC will be 0 because B and C terminals are short circuited. BC terminals are short circuited by S3 and S5, and VCA is equal to plus Vs because C is connected to plus of Vs and A is connected to minus Vs. Now for mode 6, we can write VAB equal to 0, VBC is equal to minus Vs, and VC equal to plus Vs. So we have obtained the values of the voltages of the delta connected load, VAB, VBC, and VCA for 6 modes of operation. And hence we can plot the graphs of VAB, VBC, and VCA. So the graphs are plotted here. The first waveform shows the different switches that are being conducting for 6 modes. The switches which are on for 2 cycles are shown here. This is for first mode, second mode, third mode, fourth mode, fifth mode, and sixth mode. And the different switches that are on are also shown here. And the first, the VAP waveform, it is shown for 2 cycles. We could see that VAB is equal to plus Vs for first 2 modes, and that is equal to 0 for third mode, and is equal to minus Vs for fourth and fifth mode, and is equal to 0 for sixth mode. And VBC is plotted here, whose value is equal to minus Vs for first mode and equal to 0 for second mode. Then that is equal to plus Vs for mode 3 and mode 4, and is equal to 0 for mode 5, and is equal to minus Vs for mode 6. Similarly, VCA is also drawn here. So we have seen the operation of the 3-phase voltage source inverter for 180-degree conduction mode with the delta connected load. We have also derived the voltages of the delta connected load for VAP, VPC, and VCA, and we have plotted the waveforms. So if you like this video, please do subscribe and share. Thank you.